Kia ora koutou. This video is going to go through question 2 of the end of topic test for complex numbers. So this one's got the hardest of the 3 excellence questions in it, the one that's the locus looking at the magnitudes. But first there's some quite nice, easy achieved stuff. So let's start off with looking at this one here. We've got u and we've got v, and we have to calculate u times the conjugate of v and get that in terms of k. So we can just go straight into that. U times v conjugate is equal to 1 minus 2i times 2 plus ki, which is equal to 2 plus ki minus 4i minus 2ki squared, which gives us 2 plus 2k plus k minus 4 times I. So there you go, that's the first question done. That's an achieved question, obviously. And the next one is also really straightforward, and guys, you did this really well. I think everyone got this. So when we've got polar form and we are dividing one by the other, we are going to divide the magnitudes and we're going to subtract the arguments. So that gives us straight away P over Q is equal to 2 over 6 cis of 2 pi on 3 minus pi on 2. So thinking back to year 9 fractions, this is 4/6 and this is 3/6. So that gives us 1/3 cis of pi on 6. So that's that one done. Okay, the next question was probably the worst done in the whole test. That's from my class for 13 MCA. So if you're watching this from another class, maybe you got this fine. But I think I'd gone through this too quickly in class. So to make up for that, what I've done is I have made you a special remedial worksheet. And if you go into the Dr. Frost tracker sheet, there's a link to the worksheet there. This is just the first bit. And then I've done work solutions that are in the same file. So please, please, please go and do that unless you got this question dead right and you know exactly what you're doing. Because these are really solid kind of merit problems that come up over and over. So we're finding all the solutions for z cubed is equal to this thing here. So one of the first mistakes that people made is that they didn't draw a diagram, and that meant that you got the wrong argument. So let's look at how the diagram is going to help, like every single time. Right, so negative root 8 means that I'm going back here. And then plus root 8i means I'm going up here. Right, very messy, but you can see straight away that I've got a special triangle. So two things to notice here. The angle, the argument, is formed with the positive direction. So the arg is equal to 3 pi on 4. Quite a few strong students told me that the arg was negative pi on 4, right? They are different things. Negative pi on 4 is down here. The second thing you can do, because you've got that drawn out, is that you can whack on there your root 8 length here, right? So negative root 8 here, and then root 8 here. And what we're looking at is a scaled up version of a 1, 1, root 2 special triangle. So what have we done? Well, we've taken the 1 and we've times it by root 8. Okay, so it's a similar triangle, and that means that the magnitude is also going to be times by root 8. So we can very quickly get this number here into polar form. I'm just going to whoosh over to a blank screen. So where we've got to so far is we've got z cubed is equal to 4 cis of 3 pi on 4. But remember that what we do to solve these is we say, well, that's my angle, but it's not a unique angle. So I've got all of these spin arounds that are going to generate the other two solutions. So z cubed is equal to this. Now, z is equal to r cis theta. So we substitute that in, and we get r cis theta cubed is equal to 4 cis 3 pi on 4 plus 2n pi. But then we have the beauty of de Moivre's theorem, which tells me that r cubed times cis 3 theta is equal to this. And my last step is going to be matching up those bits. So r cubed is 4. That means that r is equal to the cube root of 4. And 3 theta is equal to 3 pi on 4 plus 2n pi, giving me theta is equal to pi on 4 plus 2n pi on 3. And you know from hopefully, well, you will after you've done the remedial worksheet, that it's worthwhile making these unsimplified fractions and getting a common denominator. So let's do it out of 12. So this is 3 pi on 12 plus 8n pi on 12. Now you don't have to do that, but it's going to reduce errors later on. So now we can blast through and we can get our 3 solutions, right? We're looking for 3 solutions because it's a cubic equation. So Z1 is when n equals 0. Z1 is going to be the cube root of 4 cis just this. So 3 pi on 12, which we're going to write back as pi on 4. When we have n equals 1, we get our second solution. And that's going to be the cube root of 4 times cis of 11 pi on 12, right? That's substituting n equals 1 in there. And then the last one comes when I substitute n equals negative 1, and that gives me Z3 is equal to the cube root of 4 cis, right? 3 take away 8 gives me negative 5 pi on 12. So there you go. I think those questions are really easy as long as you don't screw up the basics way up the top. So please, please, please go and do some practice on that. Right, 2 questions to go. The next one, part D, is I think a pretty easy merit question, and then we've got this excellence one. So let's look at this one first. We've got Z here, and then W is equal to 5 over Z plus 2 minus 5i, and we have to find the argument of W. 2 ways to do this, and I'm going to show you the good way first. So W is equal to 5 over 1 minus 2i plus 2 minus 5i. So here, I'm just going to clean this up before I do anything. So we're going to have 5 over 1 minus 2i times 1 plus 2i over 1 plus 2i plus 2 minus 5i. And that equals 5 plus 10i over 1 plus 4 plus 2 minus 5i. So you can see that the working here is minimal, right? We've got 5 over 5, which is 1, plus 10i over 5, which is 2i, plus 2 minus 5i, giving me 3 minus 3i. And we need to find the arg of that. So the arg of 3 minus 3i, again, just do a sketch. Here's 3, and here's 3i down here. So the argument here is equal to negative pi on 4. The other way you can do the argument, of course, is you can do tan inverse of the y over the x, and you'll get it that way as well, right? But that you don't need to do that. If you're spotting that you've got a 3 and a negative 3, you should be getting confident enough to draw your diagram and just work out where you're sitting. So that's that question done. Now, the other way that you could do that question, and it might look tempting, but actually it works out to be kind of extra work, is instead of cleaning up this first, so instead of doing our conjugate multiplication thing, we could do kind of what we'd do in year 9, well, in year 9 if we were doing complex numbers, and we had over 1 minus 2i. So we're getting a common denominator. But if we do it that way, I'm just going to show you why it's more work. We're going to get that, right? So then we're going to have to expand the top line, and we've still got 1 minus 2i, and then we're going to have to do the conjugate thing anyway. So just, you can play with that if you want to, but I reckon, I don't know how many more lines of working it is. I think it's about 4 or 5 extras. Every time you do more working, you increase the risk that you're going to make a silly mistake. So do it the first way that I did. Okay, so forget about that. Now, I've got 6 minutes left to do this last question, and I shouldn't need that long. I'm going to do this using both algebra and a graph. I don't think it's possible to do this question without a good graph, and that's why I like it. I think it's a really nice locus problem. What we're looking for here is we're given a locus, and if you're in 13 MCA, you should look at that and straight away see that it's going to be the equation of a circle, and we're going to be shading inside the circle. But we're not interested in just finding the points. So the points we're finding are z. We want to find the possible values of the magnitude of z. So we're interested in how far is every point in my locus. So here's my z set of points. I want to know how far away are all of those points from the origin. So we'll start off with a little bit of algebra. So we'll start by saying let z equal x plus iy, and then we're going to substitute this into here. So x plus iy minus 2 plus I has a magnitude that is less than 1. Now we're going to apply, well, we're going to group up my real and my imaginary, so x minus 2 plus I times y plus 1 is less than 1. Applying the definition of magnitude, we get this. We get x minus 2 squared plus y plus 1 squared is less than 1. And now we're going to square both sides. Right, when I square both sides, I can see that I've got the equation of a circle. And the circle has got a radius of 1. And I'm just going to draw the circle nicely. Where are we? Bing. Okay, I could have done this in GeoGebra, but I don't like doing that because I guess you're going to be stuck doing it not in GeoGebra and with just a pen and a ruler. So I want to show you how a good diagram is really going to help us here. The center is going to be, and we should write this down, so the center is at 2, negative 1, or actually better, at 2 minus I, and the radius is 1. So let's just count out a couple of units. So well worth taking your ruler in with you. So there's 1 centimeter, 2 centimeters there. And then we're going to go down and do the center of the circle is going to be down here. So I'm going to just freehand draw that circle now, no doubt badly. Let's see. So we want to put those points in there because we know it's got a radius of 1. And now we're going to draw. And again, I'm not cheating by drawing a perfect circle, but that's good enough. So the points inside that are Z points. So we've got distance between the center of the circle and those points has to be less than 1. So better here actually is to do a dotted line. So let's see if we can do that. Right, because if I'm on the outside of that circle, my distance is equal to 1, not less than 1. And now what I want to know is what are the possible values of the magnitude? So take your ruler and just play with it and see where is the point that's the closest to the origin, right? So taking your ruler, looking at it like this, well, the point that's closest to the origin, you can see as I swing up, I'm getting closer and closer and closer and closer. And the closest one is going to be this one here. That point there is going to be the one that's closest to here, because I'm looking for the possible values of the magnitude. And so all of the magnitudes are going to be at least as long as this distance. And the longest they're going to be is if I continue that line and I go over to the other side here, then this is the biggest possible value of the magnitude. Now, that looks quite difficult until you notice something, which is that this is the center of the circle. And we know how long, I'm just going to change highlighter color. So we know how long this is here, or we can find it using year 10 Pythagoras. So that's the first thing. And then we know that the radius has length 1. So to find how far it is from the origin to point A, all we have to do is find that total length and then take off 1. So at A, the magnitude is equal to, well, let's figure out how long this line is. So this bit here has a side length of 2, and this bit here has a side length of 1, right? Because it's centered at 2 minus I. So at point A, the magnitude is going to be all of that side, which is root 5, take away 1. And over here at point B, that's the furthest away, the magnitude is going to be this length here, all of that, plus 1. And that means that anywhere in this area with the points, my magnitude is going to be somewhere between those two values. So they're the possible values of the magnitude, right? So between root 5 minus 1 and root 5 plus 1. Okay, so that's our final answer for that one. 20 seconds to go. I will probably do part 3 tomorrow night because I have done enough work for one night. So that should keep most of you happy. If you're still up doing maths, go and try those remedial complex numbers questions. Thanks for watching.